So in this short lecture, I want to define and investigate properties of a linear span and a closed linear span in Hilbert spaces. So let me just remind you a definition, so that if I have a family x theta, theta in I, so x theta are elements of a space X, which in this lecture will be a Hilbert space. So I have a family x theta of elements of X. Here the set I can be finite, countable or uncountable, so I is any set. Well, the linear span of the set x theta for theta in I, by definition, remember I gave already this definition, this is the smallest linear set which contains all x theta. So I have two requirements. I take all linear sets, so, and all linear sets which contain x theta, all x theta. And I want now the smallest among these sets, and I call the smallest among these sets the linear span of x theta. So this is the linear span of x theta, and we proved in a previous lecture that the linear span of x theta is given by the set of all finite linear combinations of x theta. So this is the set of all sums from 1 to m of alpha j x theta j, where m it's a non-negative integer, alpha j are scalars, and theta j belongs to I. So this is the definition of linear span. Remember, it's the smallest linear set which contains x theta, and we proved that the linear span of this family is actually given by all finite linear combinations of these x theta. And then I introduced a second definition, which is the closed linear span of this family x theta. And now, in the closed linear span, what we require is that we take all linear sets, closed linear sets, which contains the x theta, and we take among all these closed linear sets the smallest one. So this is the definition of the closed linear span. It's the smallest closed linear set which contains all x theta. And we proved in a proposition or in a lemma that the closed linear span of this x theta, that this is actually the closure of this set. So I don't rewrite these three conditions. We take this set, we take its closure, and we proved that the closed linear span of this family is given by this set. So now what I claim is that in the context of Hilbert spaces, we have a simpler characterization of the closed linear span of a set, and this is one of the main topics of this lecture. So let's start with a proposition. I know that maybe I haven't been very clear in the previous set, but I haven't been clear because we already defined linear span and closed linear span, so I didn't spend much time on the definition and the statements of these two propositions, but I invite you, if it wasn't clear, to go back to one of the previous lectures in which I defined and I proved all these identities. So here is one proposition. X will be a Hilbert space. I want to investigate the closed linear span of a family x theta, let me insist that I might be uncountable. We know that this is the closure of alpha j from 1 to m x theta j, such that we have three properties. M, it's a finite number, alpha j's are elements or scalars, and theta j are elements of I. So this is the closed linear span. And the proposition provides you necessary and sufficient condition for an element to belong to the closed linear span. So it states that Z belongs to the closed linear span of this set x theta, theta in I, if and only if, well, for all x such that which is orthogonal to all x theta, for all x such that x, the scalar product of x with x theta is equal to 0, that this implies that Z is also orthogonal to x. So in order to prove that an element Z belongs to the closed linear span of this set, it's enough to show that whatever x which is orthogonal to all x theta, it is also orthogonal to Z. If we can prove that, we know that Z is in the closed linear span, and this is a necessary and sufficient condition. So proof. So assume that Z belongs first to the closed linear span of this set. If Z belongs to the closed linear span, we know that the closed linear span is given by this expression. So this means that Z is the limit, as p goes to infinity, of one of these elements. So let me write this as a sum from 1 to m, which depends on p, mp. Then we have alpha pj, x theta pj. So since the closed linear span is given by this closure, this means that there exists an element of this set which converge to Z. Now, assume that x is orthogonal to all x theta, and let's prove that Z is also orthogonal to all x theta. Well, since Z is this limit and the scalar product is continuous, this means that Z of x, the scalar product of Z with x, by continuity of the scalar product, it's equal to the limit in P of Z with the sum. Now, since, Z is the limit, so this is actually equal to the scalar product of this element with x. Right? Z is this limit, and therefore Zx is the limit of the sequence with x. Now we know that x is orthogonal to each x theta. So by linearity, we can remove this out of the scalar product. We get the scalar product of x theta pj with x. This is 0. So all elements, all terms here are 0. So this limit is equal to 0. And from that, we get that the scalar product of Z with x, it's also equal to 0. So we proved that indeed, if Z is an element of the closed linear space of this set, then if we have an element which is orthogonal to all x theta, it has to be orthogonal to Z. Now let's assume that Z doesn't belong to the closed linear space of x theta, and I will find one x which is orthogonal to all x theta but which is not orthogonal to Z. So I'll prove in this direction by assuming that this is not true and proving that then this is not true. So let me call the closed linear span of x theta y. So y, it's a closed linear subspace of X. And I know that X is equal to Y plus the orthogonal of Y. So I have an element Z, so it can be written as an element of Y plus an element of Y orthogonal, Y perp. So Z, it's equal to, let me call U plus V, maybe, where U belongs to Y, to the closed linear span, and V doesn't belong to Y, or V belongs to Y perp. So since Z doesn't belong, Z is different from 0. Right? Because, well, it doesn't belong to this linear space. This linear space contains 0. Also, Z doesn't belong to Y, so that V has to be different from 0. Because if V is equal to 0, this means that Z is equal to U, but U is an element of Y, and I'm assuming that Z does not belong to Y. So V is different from 0. So what we have is that, well, V squared, which is different from 0, because V is different from 0, this is equal to the scalar product of V with V. But V is Z minus U, so this is Z minus U scalar product with V. And U belongs to Y, and V belongs to Y orthogonal, so U and V are orthogonal, so this is actually equal to ZV. So I have that ZV is different from 0. So Z and V are not orthogonal, but however, if you take any theta, x theta belongs to Y, right? Because, well, Y is the closed linear span of these sets, so each of these elements belongs to Y. And therefore, the scalar product of x theta with this element V is 0 because x theta belongs to Y and V belongs to Y orthogonal, and therefore they are orthogonal. So in this way, I constructed an element V which is orthogonal to all x theta, but V is not orthogonal to Z because we shown that the scalar product is not equal to 0. Therefore, if Z does not belong to the closed linear span, we can find an element X, which I called here V, which is orthogonal to all x theta, but which is not orthogonal to Z. So that proves that, well, by contradiction, that this statement implies that one, and this completes the proof of the proposition. So let me introduce a definition. I would say that a family x theta, where theta belongs to I, and again here I may be uncountable, that this is a family of orthonormal. So this is an orthonormal family, say, if, well, we have two conditions. First, I want the norms to be equal to 1. And then the second condition is that they are all orthogonal. So x theta prime, it's equal to 0 if theta is different from theta prime. So I'll say that the family is an orthonormal family if all elements have norm equal to 1 and if they are all orthogonal. So if I take theta different from theta prime, the scalar product of x theta with x theta prime is equal to 0. And then a second definition is that x theta, theta in I, is a basis of x. So basis, here it's the term I'm introducing. Well, it's a basis if, well, it's an orthonormal family and B, the closed linear span of this family, x theta, it's equal to x. So this family will be called a basis if it's orthonormal, so they are orthogonal 2 by 2 and they have all norm equal to 1. And besides, well, any element of x belongs to the closed linear span of this family. So now remark, I'm starting from a family x theta which is orthonormal. And I want to make sense of the infinite sum, of an infinite sum of scalars times x theta j. So instead of writing theta j, I'll just write xj. So I'm assuming that I have a countable now, xj, j larger than 1, which is orthonormal. And I want to make sense of this element, of the sum of an infinite sum. So we know how to make sense of finite sums. These are just finite linear combinations. So this is well understood. But now I want to define an infinite sum. And to define this infinite sum, let me assume I will define this infinite sum provided the squares of alpha j, so alpha j has its square summable. So I want to say that, well, so my claim is that assume that you have scalars alpha j and that the sum of the squares of the absolute values of the alpha j's is finite, then I can define an element x as the infinite sum of alpha j xj under the assumption that these xj are orthonormal. And the way we do that, well, is just by showing that this family, so let me call Z m, the finite sum up to m, so this is a sum from 1 up to m of alpha j xj, I want to prove that Zm it's Cauchy. And since it's, well, once I prove that it's Cauchy, I know that it converges. Zm converge to some element x, and this element x will be represented by this sum. So when I write this sum, I mean, well, the limit of this Cauchy sequence. So let's prove that Zm is a Cauchy sequence. To do that, I need to compute Zm minus Zn square, the norm square. So this is the scalar product of Zm minus Zn with Zm minus Zn. But by definition, Zm, let's say that m it's larger than n. So Zm is the sum up to m, Zn the sum up to n. So this is a sum from n plus 1 up to m of alpha j xj. So now if you use the fact that the xj are orthogonal and they have norm equal to 1, I leave it to you to compute this expression. What I claim is that this is given by the sum from j from n plus 1 to m of alpha j squared. And since I assumed that this sum is finite, it's clear that if m and n are large enough, this sum is bounded by epsilon. So whatever epsilon, I can find n0, such that if n and m are larger than that n0, this is smaller than epsilon. And that proves that Zm it's indeed a Cauchy sequence. Therefore, this sequence of partial sums converge, and I represent the limit of this sequence by this infinite sum. So when I write this infinite sum, and I'm allowed to write this infinite sum whenever this sum is finite, what I mean is the limit of this sequence, this Cauchy sequence. So now I have this orthonormal family, which sometimes I'll call that an orthonormal set. So I have this orthonormal set, and I fix x in X, our Hilbert space, and I call alpha theta the scalar product of x with x theta. And so here this family may be uncountable, so we have here an uncountable set, parameters alpha theta, but what I claim is that the set of theta such that alpha theta is different from 0, that this set is countable. It's at most countable. So though this family might be uncountable, well, the family of theta for which alpha theta is different from 0, this is at most countable. And then, okay, what I claim is that now if I take the sum of alpha theta square, since this family is at most countable, I can sum over all theta. Because actually this sum it's over a set, well, a countable set, right? Because essentially all of them are 0 unless but a countable number. So I'm allowed to consider that sum, and this, what I claim is that this is bounded by the norm of x squared. Of course, this family depends on x, so for that fixed x I have a family which depends on x. But this family, what I'm sure is that if x belongs to x, that this family is at most countable, and that the sum of the squares of alpha theta, that this is bounded by x squared. So I rewrote here what we have. We have this family. I here may be uncountable. This is an orthonormal set. So I fix now an x in our Hilbert space X. I define alpha theta as the scalar product of x with x theta. What I want to show is that, well, the family for which theta, the family of theta for which this is different from 0, it's countable, and that we have this bound. By the way, this bound, it's called the Vessel inequality. So let's prove that. So let me take a j in I which is countable. And so j, let's say that j it's equal to theta k, k larger than 1. And what I want to do is to compare from 1 to m of x, so what I called alpha theta, so alpha theta it's x theta j, x theta j minus x. I want to compute this norm. So I know that this is non-negative. And now let's compute. So let's expand that. So I leave it to you to expand. What we get, since x theta are orthonormal, is that this is equal to the sum, and let me remind you that this is what I called alpha theta j. So that this is the sum from 1 to m of alpha theta j square. So I leave it to you to perform this computation. Then we have minus 2 times the real part of the sum from 1 to m of alpha theta j x theta j x, then plus the norm of x squared. I leave it to you to check this identity, but here, so by linearity, this is the sum from 1 to m of alpha theta j x theta j x. But by, so this is 2 times the real part of this. But this, remember, we have that yx, it's equal to, by the property of the scalar product, which is skew symmetric, that yx, it's actually the complex conjugate of xy. And so here we get the complex conjugate of x theta j, but x theta j, it's alpha theta j. So here this is equal to alpha theta j, the complex conjugate. So we get alpha theta j times its complex conjugate. This gives me the absolute value of alpha theta j squared. So with that, we proved that this is, I repeat, the sum of the first term, which is sum from 1 to m of alpha theta j squared. This second term, as I said, gives me here, each term, it's the absolute value of alpha theta j squared. The sum, so, gives me a real number. So the real part, it's its number. So this gives me minus 2 times the same expression. And then plus x squared. And therefore, what we get from this inequality, we know that this expression, it's non-negative. Here what appeared, it's this term and minus 2 times this term. So from this we get that the sum from 1 to m of alpha theta j squared, it's bounded by x squared and the norm of x squared. So this holds for any m. We can send m to infinity to conclude that the sum for j larger than 1 of alpha theta j, it's always bounded by x squared, and this whatever family theta j, countable family theta j we choose. So this is the first estimate in the proof of this lemma. So whatever, let me repeat it, whatever countable subset of I, so it's countable, I can represent them by this sequence theta k, whatever countable sequence theta k, what I get is that the sum of alpha theta j of the absolute value squared, it's bounded by the square of the norm of x. So I rewrote here what we proved. If you take j, a subset of I, which is countable, then if I sum only over this countable family, what I get is that the sum of the square of the absolute values of alpha theta, it's bounded by the norm of x squared. Now let me call j of m, so let me fix a non-negative, an integer larger than 1, and let me call jm the set of all theta in I such that alpha theta it's larger than 1 over m. Well, I claim that this set is finite. Because assume, so let me take theta 1 up to theta p, assume that theta 1 up to theta p belongs to Jm. So this means that alpha theta j it's larger than 1 over m, and therefore the square it's larger than m squared. So if I sum from g from 1 to p of alpha theta j square, I get that this is larger than p over m squared by this inequality, but on the other hand, by the other inequality, we have that this is bounded by the norm of x squared. So p, so from this inequality, p has to be smaller or equal than m squared times the norm of x squared. So let me, maybe it's not clear. I have this family which is an orthonormal set. I fixed a point x in x. So I fixed that element x, and everything here is depending on this element I chose, right? Alpha theta depends on x, and these sets Jm depend on x because alpha theta depends on x. So what I'm claiming is that you fix that x, and now, while you proved for that fixed f x you define alpha theta, you prove that for any countable subfamily of I, this sum it's bounded by the norm, the square of the norm of x. And now we define this set, which depends on x, as all theta for which alpha theta is bounded below by 1 over m. And what follows from this bound is that this set Jm has at most m square x square elements. So you can't have more than m square x square elements due to this inequality. So this set, it's finite, and you have a bound on its cardinality. Its cardinality is bounded by m square x square. So it's a finite set. And now, of course, if I represented by J all the sets for which all theta in I such that alpha theta is different from 0, this set is the union for m larger than 1 of Jm. Right? Because if alpha theta is different from 0, it has to be, its absolute value has to be larger than 1 over m for some m. So this set is obviously included in that union, and that union it's included in this set. So we have an identity. Since each set Jm it's finite, its union it's countable, and that proves the first assertion of the lemma is that this set, the set of thetas for which alpha theta is different from 0, that this set is at most countable. So we just proved that if I represent by I of x the set of thetas for which alpha theta is different from 0, that this set is countable. And now, therefore, I can write the sum over all theta in I of alpha theta square, and by that, well, this might be an uncountable set, but since alpha theta is 0 for almost all, for all but a countable number of thetas, what I mean by this sum is that this is actually a sum over all theta in Ix of all alpha theta square. And now, well, since I'm doing a sum over theta in a countable family, I can use the previous result. I proved that if J is countable, the sum of theta in this countable family is bounded by x squared. So I get that this is bounded by the square of the norm of x, and this is exactly the second statement of dilemma, is that, well, the sum of all these alpha theta is bounded by the norm of x squared. And let me just mention that, well, this inequality can be strict, because here I'm assuming just that x theta is an orthonormal set. I'm not assuming that it's a basis, right? So maybe to form a basis, I'm missing some vectors, and therefore I don't have an identity, but a strict inequality. So this inequality can be strict just by the fact that I'm not assuming that x theta forms a basis, but only that they are orthonormal. Now let me state a proposition which is very useful. Let's say that we have x theta, theta in I, which can be uncountable. So this is an orthonormal set. And my claim is that the closed linear span of x theta that we have a representation of this set. This is exactly the set of all sums alpha j x theta j, where alpha j are scalars, such that the sum of alpha j, it's the square, it's finite, and theta j belongs to I. So I'm claiming that in the case of a Hilbert space, we have a very simple representation of the closed linear span of a family which is orthonormal. It is just given by this set, where here I have countable sums. We know how to make sense of such a countable sum, provided that the square of alpha j's are finite. So we know these elements, and what I claim is that this set corresponds exactly to the closed linear span. So for the proof, let me explain you the proof. I'll call this set the set A. Of course, A contains x theta, because I can always represent x theta as a sum of alpha j, the sum from 1 to 1, alpha 1 it's 1, and here I have x theta, so that's clear. So now I claim that A is closed. And if I can prove that A is closed, since this is the smallest closed linear set which contains the x theta, we will have that A is contained in this set, provided we show that A is linear. So the first thing I will do is to show that A is linear and closed to have this inequality. Sorry, the opposite inequality, right? Since A is linear and closed and contains x theta, and since this is the smallest one, this one is included in that one. So I'll start by proving this inequality by showing that A is linear and closed. So that A is closed linear, that's easy. I mean, if you have two elements of A, they are written this way, you can make sense of the sum. So I leave the details to you. What I really want to show is that A is closed. So let's consider a sequence Zn in A. Assume that Zn converge to some Z. I want to show that Z belongs to A. So Zn belongs to A. This means that Zn can be written as a sum for j larger than 1 of some factors alpha n j, x theta n j. Right, for each fixed n, the n by definition of A can be written as such a sum where the sum in J of alpha n j square is finite. Fine. So let me call In this set, the set of theta nj for j larger than 1. So this set In, it's a countable set. Let me call I the union of n of In, and I will be represented by, well, it's a countable family, so let me call it that as beta k, k larger than 1, or maybe beta is not nice, so let me call that theta k hat. So I, and this is, and of course I, it's a very bad notation because I already used it, so let me call that maybe Jn and j. So Jn is the family of theta nj for j larger than 1. J will be the union of the Jn. So this is, of course, a countable set because it's the countable union of countable sets. And now, well, this is a countable family, which I'm representing by that. So this is a subfamily of I. So J is a subset of I, which is countable. And now I can here, for each n, I can rewrite Zn in terms of this x theta hat k. So now I can change the values of alpha and j. Okay, so let me rewrite that as theta j. What I'm saying now is that I can represent now Zn as a sum over, say, k larger than 1 of alpha, we can call that beta n k x theta k hat. So some of these theta hat k will be equal to this theta j, which depends on n, theta j n. Some of them will be equal. So what I mean here is that most of these betas of these scalars will be 0, and some of them will be equal to the alpha j's, the ones for which theta hat k is equal to sum of theta nj. For all the other ones, if theta hat k belongs to Jn, this means that theta hat k is equal to some theta nj, and therefore beta nk, the beta nk corresponding will be alpha n. This has the advantage that now I have all elements Zn represented with respect to the same family, countable families of x. While in this one, for each n, I have a different family of index theta n. Now I have for all n the same family of indices. So we want to show that A is closed. So we fix the sequence Zn in A, which is converging to Z. And we were able to represent Zn as a countable sum of scalars times these vectors x theta hat k. Now I claim that Zn square it's equal to the sum of beta nk square for k larger than 1, because this family, it's a family of orthonormal sets. So we have to recall how we define these sequence. So Zn is actually the limit as m goes to infinity of the Cauchy sequence of the partial sums. So when we define this infinite sum, we proved that these partial sums form a Cauchy sequence, and we defined this infinite sum as the limit of this Cauchy sequence. Now, since Zn is equal to this limit, we get also that the norm of Zn is the limit of these norms. Because, well, the norm is continuous. Now let's compute the norm of this expression. Well, we computed it many times, so we proved that the norm, the square of the norm of this sum, so the square of these norms, it's equal, because x theta form an orthonormal set, that is actually equal to the sum from 1 to m of beta and k square. So when we send m to infinity, what you get is that this becomes the infinite sum, and therefore that the norm of Zn square is actually equal to the infinite sum. So that proves this identity. Now I want to define a transformation from these sets, so all elements which can be written as alpha or beta k x theta k hat, k larger than 1, such that the sum of beta k square k larger than 1, it's finite. So I want to define a transformation of this set to this set L2. Remember, the set L2 is formed by all sequences alpha j, j larger than 1, such that, well, alpha j are scalars, and the squares of the alpha j's are finite. So I want to define a transformation from that set to this set, a map. I want this linear map to be linear and actually to be an isometry. Recall that we proved that this set is a complete set, and I will need that. So what is the map? Well, it's very easy. You take an element from that set and you send it to, so you send an element, the element beta k x theta k to the sequence beta k. So it's clear that this is a map from that set to this set, because I'm assuming that the sum of the square of the absolute values of beta k is finite. So it's indeed a map from this set to L2. This map, it's linear. That's clear. If you take the sum of two elements, you get the sum of the sequences. So it's linear. And it's also in isometry, because the square of the norm of this element, we compute it here. It's just the sum of the squares of the absolute values, and therefore we have that if you take t of z square, that this is equal to z square, because remember, we defined the norm of a sequence alpha as the square root of this expression. So it's an isometry, and therefore we will play with this isometry in order to show that the set A is closed. So I'm running out of space, so this is why I wrote here T, our map from this space to L2. We proved that it's an isometry, and with that I want to conclude the argument. So we have Zn. Zn are elements of A, and they are converging to Z. So I want to show that Z, it's an element of our space A. So for that, I take Zn. Now I map Zn And to get T of Zn, it's a sequence which I will represent by alpha n, j. Well, this is an isometry. So this means that Zn square, it's equal to alpha n square. Now, Zn, it's converging. So this means that Zn, it's Cauchy. It's a Cauchy sequence because it's converging. Now, if Zn is a Cauchy sequence, and since this map is an isometry, this means that T of Zn is also Cauchy. So this is a sequence alpha n. But since T of Zn is Cauchy, and the space L2 is complete, which we proved already, this means that T of Zn it's converging to some sequence which I will represent maybe by beta. Now, let me define. So beta, it's such that, well, it's an element of L2, which means that the sum of beta j square is finite. Now let me call W the element beta j x theta j hat. I can make sense of this element because beta j square is finite. So this is a well-defined element of X, and actually this element it's an element of my space A because I'm writing as an infinite linear combinations of these vectors X theta hat j. Now I claim that Zn it's converging to W. Well, because this holds if and only if T of Zn converge to T of W, because T it's an isometry. But what is beta j? Beta j it's exactly T of W, right? Because we define W in this way so that T of W is the sequence beta j. And we know that T of Zn converge to this sequence beta j, which is T of W. So we know that T of Zn converge to T of W, and therefore that Zn converge to W. So we proved that Zn converge to W. Well, W is given by this sum. But Zn is converging to Z, and Zn is converging to W. So W is equal to Z. So Z is equal to W, and W it's an element of A. This proves that Z is an element of A, and therefore that the set A is closed. So we just proved that A it's a closed set. So A, remember, it's the right-hand side. So since A it's a linear and closed set which contains the x theta, it contains the closed linear span. So we proved that the closed linear span is contained in A. And now we have to prove the converse inequality. So we have to show that A is contained in the closed linear span of x theta. So let's take an element of A, x in A. So x in A means that x it's equal to the sum from larger than 1 of alpha j x theta j, where alpha j's are square summable. Fine, but now let me call xn the sum from 1 to n of alpha j x theta j. So the x theta j belong to this set. This set it's the smallest closed linear set which contains this. Well, since it's a linear set, it has to contain x. these linear combinations of x theta must belong to the closed linear span because, well, any linear set which contains x theta has to contain these finite linear combinations. And, well, we have seen, since the alpha j's are square summable, that xn converge to x. The partial sums converge to x. This is the definition of this element. Well, since the closed linear span is closed and contains xn, it has to contain x, and this proves that if x is in A, then x belongs to the closed linear span of x theta, and therefore we have proved the other, the converse statement, and therefore these two sets are equal, and that completes the proof of the proposition. So let me conclude this lecture with a remark. So X, it's a Hilbert space. X theta, an orthonormal set. In the proof of the previous proposition, we've seen that if I have X, which can be written as alpha j x theta j for some j larger than 1, then, and where here I'm assuming that the alpha j's are square summable, then we proved in this proposition that the norm of x is actually equal to the sum of the alpha j square. So that will be used, that's an important identity which will be used many times, so it's important to detach it from the proof. So we have this identity whenever you have x which is given by this sum for alpha j's which are square summable, then the norm of x is equal to the sum of the square of the alpha j's. And what are the alpha j's? What I claim is that alpha j is actually equal to the scalar product of x with x theta j. And why is that so? Well, remember that x is the limit in M. The definition of x is as the limit in M of the partial sum. So by continuity of the scalar product, x of x, the scalar product of x with x theta k, since x is the limit, this is the limit in M of the scalar products, so x with, x is the limit, so this is the limit of sum from j1 up to M of alpha j x theta j x theta k. So this is the limit in M of the sum, j from 1 to M of alpha j x theta j x theta k. But the x theta j x theta k are normal, so this is equal either 0 if j is different from k or 1 if j is equal to k. So let me represent that by delta gk, which is either 1 if j is equal to k or 0 if j is different from k. So if for all m larger than k, this sum is actually equal to alpha k. So this limit is alpha k, and from that we get that alpha k is indeed the scalar product of x with x theta k. So this is a second observation, that alpha k is actually the scalar product of x with x theta k in this representation. So these two facts will be used many times and deserve to be remarked or observed detached from the proof of the previous proposition.